So we're going to think about gas flow through capillaries. Oh, that was a really bad segue. All right, viscous flow in a capillary. I want to introduce this because this is a kind of important when you're working with these continuous flow techniques to understand the physics of gas moving through a small tube, a narrow tube. And the flow is described, the volumetric rate of flow is described with the Poiseuille equation, where you have a change in pressure across the length of the tube, the distance, and then the viscosity of your gas. And what's really important here to note is that the flow is a function of the radius to the fourth power. Say that with me now. Radius to the fourth power, right? So if you swap out a tube that's slightly bigger or smaller, just thinking it won't matter, it will matter, right? It does matter. So that's something to pay attention to when you're working with these systems. You can actually use the diameter of the tubes as kind of a resistor, as a way to slow flow down if you want to. It's a very powerful sort of understanding to have. The other thing I will point out in this equation is the viscosity. And the viscosity of gas changes with temperature. So when things get warmer, what happens to the viscosity of gas? Does it go up or down? Does it get more viscous or less viscous? Less viscous. Who thinks it's more viscous? Does gas get more viscous or less viscous when it gets warmer? Like everybody's thinking about the story of Little House on the Prairie, where they pour the maple syrup on the snow and then it gets cold and more viscous, right? What happens with gas? When it gets cold, does it get more viscous? Like the maple syrup in the snow? It's actually the opposite of liquids. When gas gets heated up, the molecules are moving around faster and they're bumping into each other, and the behavior is more viscous when it's hotter. Isn't that cool? Right? So it gets more viscous. It's slow. It becomes harder to move it through a tube when it's hotter, because those molecules are dancing around to the beat of their own drum, right? They're not paying attention to where you want them to go. It's kind of like small children. So as you're moving gas through a tube and you heat it up, your flow rate will drop for the same if you don't change the pressure. So again, something just to be aware of. And so modern instruments, modern GC systems will have a flow control in their, some measure of flow control in their inlet system, which is basically compensating by raising the pressure. You can't actually control flow, but you can increase the pressure. And so as the GC warms up, the flow will drop. The systems will compensate by raising the pressure. And this sort of, I just find this a really useful image, and so I included it in your notes for you to sort of hang on your desk or something. This is the hydraulic analogy between electric circuits or water or movement of fluids and electric circuits. And so you can have a system where you pump liquid up into a higher reservoir, and then it flows downhill and it runs a turbine, it releases work or energy, and then you can have that flow kind of come back and then pump it up again. And that's analogous to a battery, which has sort of a reservoir of energy, and then it can flow downhill and run your light bulb and then come back up into, you can turn it on or off the way you have these valves here, and you have these throttles which are behaving like a resistor. So things that change the rate of flow in a system are behaving kind of an analogous way to a resistor in an electric circuit. I don't want to belabor this, but I just included it because I think it's a really useful thing for you to have as a reference. Okay. So continuing our journey under the hood here, this is a diagram of a gas chromatograph. We have some kind of injector where we introduce our mixture of compounds. This slinky here is not a slinky, it's not a spiral, but it's actually a capillary tube. It's an open tube, and then it has some kind of detector. In the world of analytical chemistry, the people who work with gas chromatography kind of see mass spectrometers as detectors. And the people who work with mass spectrometers kind of see gas chromatographic systems as inlets, right? So they have, it depends on what you're interested in, but in my world, I like both. So we have mass spectrometers as detectors, but we also have capillary columns as inlet systems. So let me show you a cross-section. I am actually trained in geology, so I like cross-sections. But this is at a different scale than you normally see in your geologic cross-sections. These are different kinds of columns that you will encounter in gas chromatography. The original forms were these packed columns. They're still used today, particularly for gases. The advantage is that they give you a huge amount of surface area for your gases to interact with, right? Just massive amounts of surface area. The open tubes give you a lot less surface area, so we compensate by having longer columns, typically. And you can have on your tube a coating, a bonded organic coating. It's kind of like a little layer of liquid on the inside of these columns. And the molecules can interact with that little layer, and that can enhance your separation techniques. So this is the taxonomy of columns in GCs. The way these work is similar to any kind of chromatographic system. You have a moving phase. In our case, it's a gas, but in liquid chromatography, it's a liquid. You get the idea. And you introduce a mixture, which I've indicated with 3 colored bands. And then as you go through time, some flow faster than others. And eventually, over time, you have complete separation of the components in your mixture. Okay, so that's how chromatography works. Molecules interact with that stationary phase. Remember that little liquid coating on the inside of the tube. And remember, we're kind of heating it up gently, so the boiling point is helping us with this separation. And they get into that carrier phase, and they move. Compounds with a stronger affinity for the stationary phase will stay put. Things that are more volatile and have lower chemical affinity for the stationary phase will move through more quickly. And so you can play with physical properties like boiling point and chemical properties like affinity for the phase to tailor and improve your separation. Yes?
What are common porous layers used, like around in the tube?
Sorry, this one?
Yeah.
Yeah, that's used in gas separations, where it's the mineral matrix of this is like a polar interface, and so you can have interactions with like CO2 gases. So it tends to be not used in biomarkers or hydrocarbon work like I do, but you can use it with smaller compounds, particularly if they have a strong dipole moment. Okay, good question. In the lab, you might have done work like this, where you introduce a mixture and you can sort of watch it flow through. This is a cartoon illustration of that. It's the same principle. We have, in this case, a movement of liquid through, and then a stationary phase is some kind of silica gel or alumina of some kind, where our molecules are interacting and deciding, do they want to move or do they want to stay put, right? And so you encourage them gradually to change how they feel about that, so that you kind of separate one compound from another. Not to anthropomorphize chromatography, but that's kind of how I think about it. I'm like, come on, you can do it. Here's another cross-section. This is a longitudinal cross-section of a GC column, just to illustrate this a little bit more. You have the compounds in the gas phase are going to move. The compounds that sit down, and this is not to scale, but that really thin layer of liquid on the inside of the tube, and they will sit down in that, sort of hang out, and then they're actually kind of moving back and forth between these two phases continuously, and the more time they spend in the gas phase, the faster they're moving. The more time they spend in the liquid phase, the more slowly they're moving. So in the end, when you're setting up to do some analyses using chromatography, it's very powerful if you understand some of these principles, because you can think then carefully about the chemistry of your compounds. Are you looking at hydrocarbons? Are you looking at amino acids? What kind of functionalities do you have? And so that allows you then to pick a bonded phase of your column based on the types of chemistry you want to retain and want to move through. And then you can sort of develop a temperature program that gradually increases the ambient temperature, so that the bigger compounds become more likely to go into the gas phase over time. That's illustrated in this next slide, where we have 2 chromatograms. One is done what is called under isothermal conditions, so it's always the same temperature throughout the run. And the second one is a programmed temperature, where you're gradually heating up the GC environment. So under the isothermal, you can see here, this is C10, 11, 12, 13, 14, 15, right? So the C15 is not really volatile, and it's just kind of, all right, if I have to, it's coming out like really late. Whereas in this lower one, it's temperature programmed, so as the run is going forward, as the carrier is moving through, the temperature is also increasing, and so as it increases, you're now reaching the boiling points eventually of each of these components, and here's C21 all the way out there, and you've got nice sharp peaks, and they're coming out kind of smoothly and quickly. Yeah.
What are the first two peaks before the C10 on the top? Is that the salt?
They're not labeled. I suspect they're probably these other compounds down here, just because I think it's the same mixture. So we don't even get to 21 out here, right? So that programming that you do with the GC is really, really, it gets your work done in the time of getting your graduate degree, right? It's really helpful. Yes.
Is there a reason you choose isothermal over temperature? Is everybody kind of moved to the?
There's sort of some nuanced reasons why you might slow down your programming, which I'm happy to talk to you about separately. But it is a way to kind of enhance separation.
Yeah.
It's if the differences are really subtle and you want to rely more on the chemistry of it. And if you have really simple mixtures, because then you don't have to go through all the mechanics of heating and cooling again between runs. Ready for some higher math? It's Friday morning, like, don't give us math. Well, it's okay. This is about as much math as I can handle on a Friday morning, so here it is right there. This is this really powerful metric called resolution. And I want you all to know this because, well, it's insanely simple, but it's also really, really powerful. And the separation is measured by this distance, or so the difference in time that they elute divided by the average width of a peak. And so you can run your GC, your sample through a GC and measure this. It's not hard. And then you can tweak the conditions, maybe the ramp rate or maybe the flow rate, and then see if you've improved your separation. And it's a really nice and very standard way to handle kind of the tinkering of conditions to optimize for a particular application. So if you're working in a lab where there's a GC and some other student has been running it and they hand it off to you and you think, oh great, I'll just use their conditions. Well, now you don't have to, right? You can measure your separation and decide, is that right for my samples? Can I tinker with the conditions and make this a little bit better?